let's go ahead and take a look at the enthalpy of formation value. So enthalpy of formation is represented by this delta naught sub F symbol here. Now, standard enthalpy of formation is the change in enthalpy from a reaction that forms 1 mole of a specific compound from its basic elements with all the substances in their standard state. And so what do I mean by standard state? Standard state means a substance that's in its pure form at 1 atm and 298 Kelvin. So if I have a situation in which I have reactants that are elements in their standard state that give me 1 mole of product, then the enthalpy of that reaction, the change in enthalpy of that reaction, will be equal to the change in enthalpy of formation. So what we need to understand is that the enthalpy of formation values that we obtain are all reported at a specific pressure and temperature, which is 1 atm and 298 Kelvin. And basically, these enthalpy of formation values are categorized into tables, as seen here. And basically, they're expressed in kilojoules per mole, and they relate directly to the substance or substances that are involved in the reaction, whether reactant or product. And when you're using standard enthalpy of formation values and you're looking for substances in the standard state, you're going to want to pick the most stable option. And the most stable option is going to be the one that has a enthalpy of formation value that's closest to 0, or that is 0, excuse me. So if we go over here and let's see, manganese is one of the reactants, right? If manganese is one of the reactants, in this case, this table has 2 options for manganese. It has manganese solid and manganese in its gaseous state. The manganese with the delta heat of formation, or enthalpy of formation, excuse me, value that's equal to 0, that is going to be your standard state situation. So now that we understand the standard enthalpy of formation tables and how to actually select the appropriate substances in their standard state, let's go ahead and look at a few more details. So identifying reactions that actually can represent the standard enthalpy of formation, we have to follow a few rules. First things first is that a reaction, in order for a reaction to be an enthalpy of formation representation, you have to have a single mole of product. The next thing you need to have is that elements used to make the product must be in their most stable form, and you must have a single product. So the quantity of your product, the number of products, as well as the elements utilized all dictate if the enthalpy of formation values can be utilized. So now, remember we talked about these delta H formation values. Now they can be found in an appendix, usually in the back of the book, and basically you can utilize these for calculations. We'll look at that in a minute. For now, let's go ahead and decide if the following reactions seen here actually represent a standard enthalpy of formation. Okay, so if we go ahead and we look at this first problem, okay, so first things first is criteria A, 1 mole of product. There is a single mole of product here, so far we're good. Okay, elements used to make the product must be in their most stable form. Okay, so if we go into the appendix, we will see that the enthalpy of formation value for sodium in its solid state and O2 gas in its gaseous state are both equal to 0, and those are as stable as you can get with respect to those 2 elements. So criteria number 2 has been met. Elements that are being used in this specific reaction are in their most stable form. The third requirement is that the single product is present, and there's only 1 product, so that makes sense. So in this case, the enthalpy value for this reaction can be calculated based on the enthalpy of formation values present. And we'll talk about these calculations later, but for now we can actually utilize this information to apply this type of approach. Now let's go ahead and let's look at this example here. So first things first is it says 1 mole of product is the requirement. If we look at the amount of product we actually have 2 moles. So at this point, this equation cannot be utilized to make this this equality. All right, your delta H of this reaction cannot be directly correlated to the delta H of formation. Okay, so the other requirements, element used to make the product must be in their most stable form. If we go on the table or go into the appendix, potassium in its liquid state is not the most stable form. The chlorine gas, however, is. So in order to make this reaction acceptable, we'd actually have to change our first reactant to the solid state because that's the most stable form. And we'd also have to divide all the coefficients through by 2 in order to get the appropriate equivalence. And of course, we do only have a single product, so that requirement was met there. So if we go ahead and we look at this third reaction, okay, first of all, 1 mole of product, okay, there's way more than 1 mole of product, and there's also multiple products. So requirements A and C are not being met. So this reaction, in order to make this correlation, would have to be flipped. Okay, and once we flip that situation, notice that we have 1 product. Okay, 1 mole of product, and we have a single product, so A and C have now been met. Now, in terms of the elements used to make the product being the most stable, graphite and diamond need to be exchanged because diamond is not the most stable state option for the enthalpy of formation values in the table. Okay, so in order for correlations like this to be made, you need to fit and follow these 3 requirements. You may need to use the appendix with the delta H of formation values or enthalpy of formation values in order to make these assessments. Now, why do we even care about the enthalpy of formation values? Well, because we can make the correlation between our enthalpy of formation and our delta H of reaction, we can utilize the information from the tables in order to correlate these two. So there's 2 options for solving problems that correlate your enthalpy of formation and your enthalpy of reaction problems. First things first is you could use Hess's law and the enthalpy of formation values that are associated with the appendix. And option number 2 is you use the equation seen here in order to calculate your delta H of reaction from these enthalpy of formation values. So let's go ahead and look at a few practice problems. So the first option here allows us to utilize Hess's law in concert with the enthalpy of formation values associated with components necessary for this reaction type. Okay, so we're going to use our skills that we acquired to calculate Hess's law and the correlation that we learned about earlier in order to figure out the delta H of reaction for this overall reaction. Okay, so first of all, we've been given our enthalpy of formation values and equations for C3H8, CO2, and H2O. Notice these are all either reactants or products associated with the reaction that we're actually looking to solve for. So just like we did in the previous Hess's law equations or calculations, we're going to make sure that we flip and multiply and do everything we need to do in order to sum to the overall equation above. So once again, C3H8, that's a reactant, so we know we're going to have to flip this equation. If we flip this equation, we know that the sign is going to change. Okay, so down here we've done that. Okay, notice I put a negative on the outside for that delta H formation value. Okay, so a negative times this negative is going to give us a positive value. CO2, notice that that's a reactant, or excuse me, that's a product on the overall equation that we're looking to solve for. So the CO2 is on the correct side. However, the quantity is incorrect. Now, remember, this is an enthalpy of formation expression here. Okay, so we expect only one equivalent or 1 mole to be present there. However, when we utilize this with Hess's law, we know that we need 3 moles. So we're going to go ahead and we're going to multiply through everything by 3, including our delta H of formation value for that CO2. So 3 times this value is the number we'll end up getting. If we look here at this last enthalpy of formation expression that we have here, H2O is what's present. It's on the correct side because it's a reactant, so everything should be good with that respect. However, the quantity is once again incorrect. We're going to need 4 equivalents, so the overall equation needs that, so we will multiply this enthalpy of formation expression by 4. So we've made the appropriate adjustments. If we sum both sides and cancel out whatever is left, we will end up with this equation, which matches the above. Okay, and what we know from the Hess's law approach that we've done before is that we can sum all the delta H values here to give us the overall delta H of reaction. Okay, so what are we going to do? Well, we're going to plug in the values here into this expression. So delta H of reaction is equal to the enthalpy of formation value after the reversal. So we plug that in. Same thing here and here. So we plug the appropriate numbers in. Okay, so this goes here. So negative 103.85. Okay, here's 3 times that value. So 3 times the negative 393.5 plus 4 times the negative 285.8. Okay, we multiply those out, we sum all the sum all the values, and we end up with this number for our overall delta H of reaction. So what we've done here is we've taken enthalpy of formation expressions and their values, and we've adjusted them to match the equation up here in terms of quantity. We've also flipped anything that's necessary in order to get a reactant on the correct side or a product on the correct side, just like we would do with any other Hess's law situation or any other Hess's law equation. So this is one approach to solving these problems. This would work very nicely if you were not given an appendix and you were just given these enthalpy of formation expressions. You would just treat it like a normal Hess's law problem and make all the appropriate adjustments. Now, there's another way to solve these types of problems. So this same problem, they're wanting us to solve for delta H of this specific reaction. Okay, same reaction, same concept. However, they haven't given us those enthalpy of formation expressions, so we don't have any flipping or Hess's law to do. However, they've told us that we are allowed to use the delta H of formation, the enthalpy of formation values from the back of the book. So what we would do is basically take the sum of our enthalpy of formation values for our products, subtract that from the sum of enthalpy of formation values for our reactants, and that will give us the overall enthalpy of reaction. So what we would do, products in this case are CO2 and H2O, gaseous and liquid state. So we would go to the back of the book and get those numerical values. Okay, we would do the same thing for our reactants. Okay, so C3H8 in the gaseous state and O2 in the gaseous state, we would get those numerical values. Now, what I want you to notice about the setup that I have here, okay, the coefficients are dictating the amounts of each of the substances. So notice for O2, the coefficient is 5, so I'm multiplying the enthalpy of formation value by 5. The coefficient for C3H8 is 1, so I'm multiplying by 1. I'm leaving it B. Okay, same thing for H2O and CO2. So we then plug the enthalpy of formation values into this portion of each of those spaces, okay, and you end up with what you have down here. Notice these numbers have been plugged in, boom, 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 okay, nice and clean. You multiply out, okay, do the appropriate addition and subtraction, and you get this value overall. So notice, kilojoules, it's what you should have. So this is basically the exact same value as you got on the previous example. However, in this case, you're not adding up reactions, individual reactions, or formation values. You're taking information from an appendix and plugging them into the equation above. So, pretty straightforward. Either way is correct, but basically you need to work with whatever you are given.